Hello guys and welcome into another video. Today we will study the properties of derivatives, and in particular we will study what happens when the derivative at a single point is positive. And we need to be very cautious in this because there's a property that says that if you have an interval and in that interval the derivative is positive, then the function is increasing in that interval. Well, this property is usually mistaken with a previous one that we will cover today, because if you have that the derivative is positive at a single point, then it implies literally nothing over the fact that the function may or may not be monotonous, increasing or decreasing, whatever. So we will check that, and we will study an example point that will show us why it doesn't happen. So it's like a counter example of that belief that is not actually true. So let's get into it. All right, so let's write our theorem here. Theorem. So let some function f defined on a subset of the real numbers into the real numbers be differentiable and differentiable to the right. So remember that when a function is, well, it is defined on a domain, and at a point, that point could be an accumulation point or may not be. So if it is an accumulation point, it can be an accumulation point to the left or to the right. And if it's both at the same time, then we can talk about differentiable left and right at the same time, or just differentiable. But if that point is just an accumulation point to the right, then it only makes sense to talk about a differentiable to the right, or of the right derivative of that function at that point. So we will be very explicit on that here. This function is differentiable to the right, explicitly to the right. To the right, of course, at a point to the right of this point here, that is, so this is what I was telling you earlier. So this is a set of, this is the subset of all of the accumulation points to the right. All right. Now, if so, the right derivative of f at a is positive, then the following happens. There exists some delta positive such that for every element of the domain that is inside of this neighborhood to the right, and we write that as then all right, so this is the theorem. Let me put this a little smaller. All right. So yeah, this is our theorem. As I told you, it doesn't say that the function is increasing to the right. It's not saying that. Why? So let's do a little graph here. Let's put it with this one. All right, so we have our point here, a. So this is f of a, and this theorem is telling us that to the right, once again, let me put it with another color, maybe this one, we have some x in this neighborhood, and f of x is bigger than f of a. And so does it mean that it is increasing? It is increasing to the right. Well, what does it mean to be increasing to the right? So what happens if it is, you know, always bigger than always bigger than f of a, but it is not monotonous at any point. So yeah, everything is bigger than this level line, but it doesn't have that behavior of being monotonous. So it only happens that at a it is like the smaller a value of that of the function, of that periodic function. So it's telling you nothing about that. And it will be a different scenario if you had that the function had a positive derivative or I derivative in an interval, as I was telling you previously. But this is not what is happening here. We only have that it is positive at a single point. So this is the remark that I wanted to make clear, because I've seen some grad students that are still mistaken with these points. So we need to be very clear about that. So let's write a proof here. It's very short. All right. So as always, this is just by definition. Let's put it at limit. Of course, it's going to be the limit to the right. Divided by, of course, the difference. And this is by definition our positive, yeah, this right derivative. Alright, and to complete this part, we just need to recall that if the limit of a function is bigger than some value, then that means that there exists a neighborhood for which, let's call this some function, this whole thing, this whole quotient is some function g. So there exists a neighborhood of, in this case, a right neighborhood of a, such that g of x is always bigger than 0. So that's a property of limits. So then this means that there exists some neighborhood to the right of a, such that, let's write it properly, for every x in the domain, such that this means that, and since a is always bigger than, I mean x is always bigger than a, because x is going to tends to a from the right, then this means that this term here is negative. And if it is negative and this whole thing is positive, then this means that this difference is positive. So this means that is bigger than, and this is exactly what we wanted to prove. All right. So now we will give an example to show, a counter example to show that it doesn't mean that the function is monotonous increasing in any neighborhood to the right of a. So let's check a counter example here. You know, when we are working with counterexamples in real analysis, we usually call this function the function's sine of the inverse of x. So this is kind of our best friend in counterexamples. But sometimes it is not enough to this function is not enough. I mean, it's not quite the property that we need to show, and so we put an x besides our sine of the inverse of x. But sometimes that is also not enough, and in those cases we put some little square there, and in this case we will add some positive value. So just for the sake of making sure that the derivative at 0 is positive, we will see why this happens. And as always, this is defined when x is different from 0, and then with x equal to 0. So let's call some function f of x like that. You can check that this function is differentiable at every point and with x different from 0, so that holds. And we need to see what happens at 0. So first of all, we need to check that these exist, and we will this is the same as checking that this limit exists, right? But you know that at 0 f is 0, so this disappears, and the thing above this, so this is equal to so this will be x sine sine, and then we will add, oh wait, I forgot to add x here, so yeah, it didn't make any sense otherwise. So this will be plus a half. Yeah, this is how it's meant to be. So yeah, with that correction, now it makes sense. So at 0, this tends to 0, and this is constant, so this is positive. Since it is positive, then by our previous theorem, this will mean that there exists in the right neighborhood of 0 in which every element is bigger than f of 0, which is 0. So there exists a neighborhood of 0 to the right such that every element is positive. Every value of f is positive. So yeah, does this mean that it is monotonous increasing in that neighborhood? It doesn't, because you know that what's the derivative whenever x is different from 0? So we use just the rule, the usual rule. So let's copy that here, and this is our function, and we start deriving sine, and then we add the derivative of sine is the cosine, the inverse, and then the derivative of the inverse of x is minus, this cancels out, plus a half, and this is equal to cosine of the inverse of x, a minus cosine of inverse of x plus a half. So for some values of x, this thing will be positive, because cosine could be minus 1. The cosine could be minus 1, and so this will be minus a half, but for some values. And for other values, this could be 3/2. So this derivative goes on and on. So it's positive, negative, 0 at some points. Whenever x is approaching 0 from the right. So given that the derivative values change, it goes from positive to negative, it doesn't make any sense that the function will be monotonous in any neighborhood of 0. So yeah, this works as a counterexample of that belief that I told you earlier. So even if you have your nice point here with positive right derivative, it doesn't mean that the function is monotonous increasing in some neighborhood of that point. That happens whenever it is positive in a neighborhood of that point. But if it's just in a single point, then you need to be very cautious. You need to show that it holds in a neighborhood, in an interval that contains A. Otherwise, you cannot say anything else. Alright, this is it for today. If you have any questions, you can put it down in the comments below and I will try my best to check them. Thanks for watching until now. See you later.